Have you ever wondered who first thought of talking to machines? Not with your voice, but with logic and symbols. Today, we type on keyboards and see magic on screens, but where did it all begin? To find the answer, we have to travel back in time, to a world without computers, screens, or the internet. It was a world powered by steam, gears, and human ingenuity. The most complex machines were clocks and music boxes, running on pure mechanical genius. Imagine a time before electricity was common. Everything ran on physical force. If you wanted something done, you built a clever machine with levers and pulleys. Logic and mathematics were tools for scientists, not for everyday machines. People wrote instructions for other people, not for machines. But the idea of writing instructions for a machine, that was revolutionary. Automation was a dream, every nail hammered by hand, every cloth woven by artisans. The world was full of repetitive tasks, and people craved efficiency. Mechanical devices could perform specific tasks, but they weren't programmable. To change their function, you had to rebuild them. The stage was set for a big idea. Could a machine follow instructions? The answer didn't come from a computer scientist or an engineer. The story of programming starts with threads, fabric, and a desire to create beautiful patterns more easily. The first spark of programming came from the world of textiles, where art and industry collided.
Early 19th century France. The textile industry was booming, but weaving intricate patterns was slow and difficult. Master weavers needed assistance to lift hundreds of threads in the right sequence for every line of a pattern. Joseph-Marie Jacquard saw this problem and had a brilliant idea: automate the process. His invention, the Jacquard loom, used a series of punched cards. Each card represented one row of the pattern. The loom's rods would pass through holes in the cards, lifting specific threads. No hole? The rod was blocked, and the thread stayed down. By chaining cards together, the loom could automatically weave complex designs over and over. These punched cards were the world's first program, each card a line of instruction, the sequence a complete program. You could change the pattern by swapping out the deck of cards. No need to rebuild the loom. For the first time, a machine was controlled by removable, stored instructions. The information, the pattern, was separate from the machine. This concept is fundamental to modern computing. The Jacquard loom transformed textiles and inspired a brilliant English mathematician. If cards could control threads, maybe they could control numbers in a calculating machine. The simple punched card was about to leap from weaving patterns to performing mathematics. The groundwork for the first computer was laid. London, 1830s. Meet Charles Babbage, a frustrated mathematician. Mathematical tables were calculated by hand and full of errors. Babbage dreamed of a machine that could calculate perfectly. His first design, the difference engine, was a massive mechanical calculator. But Babbage wanted more, a general-purpose computer, the analytical engine. It had all the essential parts of a modern computer, built with gears and steam. How would you program it? With punched cards inspired by Jacquard. Babbage's vision was ahead of its time. Technology couldn't keep up, and many thought he was a crackpot. But one person understood: Ada Lovelace. Daughter of Lord Byron, Ada was passionate about mathematics. She saw the analytical engine's true potential, not just as a calculator, but as a creative machine. Ada translated an article about the engine and added extensive notes, 3 times longer than the original. She realized the machine could manipulate anything representable by numbers, symbols, music, even art. Ada saw it could be a creative partner, not just a number cruncher. She imagined a future where machines could compose music or create art, given the right instructions. Ada's vision was breathtakingly modern. She understood the real power lay in the instructions we give machines. The story of programming was about to take a giant leap. In her notes, Ada Lovelace did something remarkable. She wrote a step-by-step sequence for the analytical engine to calculate Bernoulli numbers. This was the world's first published computer program, an algorithm for a machine. She described storing values, performing operations, and repeating steps, a loop. Concepts like variables and loops, the bedrock of programming, were born here. Ada invented them over a century before the first electronic computer. She's considered the world's first computer programmer. Ada saw machines as tools for creativity, not just calculation. Sadly, the analytical engine was never built in their lifetimes. Ada died young, her work nearly forgotten. But the idea of a programmable machine was out there, waiting for the right technology. The seed of coding had been planted. Fast forward a century to World War II. The military needed fast calculations. Human computers couldn't keep up. Enter ENIAC, the first large-scale electronic computer. It filled a room, weighed 30 tons, and used over 17,000 vacuum tubes. ENIAC was fast, but programming it was a nightmare. There was no language, not even a keyboard. To program ENIAC, engineers had to physically rewire it, plugging and unplugging hundreds of cables. Every logical step was a physical connection. A single mistake could ruin the calculation, and finding errors was maddening. The women who programmed ENIAC were pioneers, wrestling with this complexity daily. It quickly became clear this method was unsustainable. The solution? Store the program in the computer's memory, just like data. Now, to change the program, you just change the information in memory. This breakthrough paved the way for programming languages. The era of programming with wires was ending. The age of code was about to begin. Stored program computers ended the nightmare of rewiring, but programming was still tough. The first languages were machine code, just ones and zeros. Programmers wrote long strings of binary, nearly impossible to read or debug. Assembly language was the first step forward. It replaced binary with short words, mnemonics like ADD or store. An assembler translated these into machine code. Programming became more readable, and you could add comments. It was still tedious, but a world away from raw binary. Assembly let programmers focus more on logic, less on hardware. But the real revolution was still to come. Languages closer to human speech. Programming was about to become accessible to many more people. The next leap would open the door to the masses. The future of code was about to get a lot more human. The next leap came from Grace Hopper, a Navy Rear Admiral and computer scientist. Working on the UNIVAC I in the 1950s, she had a radical idea. Programs should be written in English-like language. Many said it was impossible. Computers only understood numbers. Hopper didn't listen. She and her team created the compiler. A compiler translates high-level, English-like instructions into machine code. Now, a programmer could write subtract tax from pay instead of dozens of assembly instructions. Hopper's first language, Flowmatic, used English keywords for business tasks. For the first time, business experts could read and understand code. Programming became about solving problems, not managing hardware. Hopper's work proved you could create a layer of abstraction between human and machine. Every modern language owes a debt to her vision. She even coined the term debugging after finding a moth in a computer relay. Grace Hopper changed programming forever. The compiler opened the floodgates for new languages in the 1950s. Two of the most important were FORTRAN and COBOL. FORTRAN, for scientists and engineers, made writing equations in code almost as easy as on a blackboard. It turned computers into ultimate scientific calculators. COBOL, influenced by Hopper's Flowmatic, was for business, processing payroll, bank records, and more. Its English-like syntax made code understandable to managers and accountants. FORTRAN and COBOL showed that languages could be tailored to specific needs. You didn't need one language for everything. Specialization made programming more accessible and powerful. These languages built the world's infrastructure, from banking to space missions. Incredibly, some of their code still runs today. The age of specialized programming had arrived. What does this history mean for us today? When you write Python or JavaScript, you're part of a 200-year-old story. Variables? Ada Lovelace's idea. Loops? Inspired by Jacquard's punched cards and Ada's algorithms. Separating instructions from hardware? That's Jacquard's legacy. General-purpose machines? Babbage's dream. English-like code? Grace Hopper's gift. Coding isn't just typing symbols. It's joining a tradition of human ingenuity. Each language was born to solve a real problem, from weaving cloth to running the global economy. Writing code connects us to weavers, mathematicians, engineers, and pioneers. Programming is a creative, human act. Logic, language, and problem-solving combined. We build on the ideas of those before us to create something new. The story of coding is the story of human curiosity and our drive to build better tools. And that's a story worth knowing.